The melting process is the foundational step in producing ductile iron pipes, where scrap metal is transformed into molten iron with the precise composition required for pipe manufacturing. This stage relies on high temperatures, careful material selection, and controlled chemical reactions to produce a base iron that meets quality standards. The primary raw material used is shredded scrap metal, typically sourced from recycled automobile bodies. The metal is delivered to the plant in large volumes by tractor trailers and transported to the melting area using magnetic cranes. The melting takes place in a cylindrical vertical furnace known as a cupola, which operates continuously to maintain production flow. Inside the cupola, the scrap metal is layered with coke, a high-carbon fuel derived from coal. Coke provides the high temperatures needed to melt the scrap metal, and also adds carbon to the molten iron. Small amounts of limestone are introduced to act as a flux, helping to remove impurities. When heated, the limestone reacts with these impurities, forming slag, a lighter byproduct that separates from the molten iron and is skimmed off at the furnace's tap hole. To sustain the high temperatures required for melting, hot preheated air is blown into the base of the cupola through nozzles called tuyères. This air ignites the coke and ensures efficient combustion. As the scrap metal melts, it descends through the furnace, picking up carbon and sulfur from the coke. The molten iron exits the cupola through the tap hole, where it flows into a ladle. At this stage, desulfurization is performed to reduce sulfur content, a critical step for achieving the ductility needed in the final product. Lime is added to the molten iron, and the mixture is vigorously stirred to remove sulfur as slag. This desulfurized iron is then transferred to a holding vessel, where it undergoes further treatment, including magnesium addition, to prepare it for the next stage of production. The casting process is a critical stage in the production of ductile iron pipe, where molten iron is shaped into its final pipe form using the centrifugal casting method. This highly controlled process ensures uniform pipe dimensions, strength, and structural integrity, making it suitable for demanding applications in waterworks and other infrastructure. The casting process begins with the transfer of treated molten iron, which has been desulfurized and enriched with magnesium, into smaller pouring ladles. These ladles hold enough molten iron to produce several pipes before requiring refilling. Simultaneously, sand cores are prepared to shape the pipe's bell, socket, and gasket seating area. These cores are made by mixing sand with a resin binder, which is heated in a mold to harden the core. The finished sand cores are cleaned and inspected before use. Each casting machine consists of a horizontal cylindrical steel mold that rotates at high speed. The sand core is placed into the bell end of the mold, and the mold is prepared for pouring. The molten iron is poured from the ladle down a chute into the mold, starting at the bell end. The mold assembly moves along a track, pouring molten iron continuously while forming the pipe's barrel. The centrifugal force generated by the high-speed rotation of the mold pushes the molten iron against the mold walls. This force ensures a uniform thickness of the pipe wall while expelling lighter impurities, such as slag and gases, toward the pipe's interior surface. These impurities have minimal impact as they remain within the pipe's wall and do not affect structural performance. The inside of the mold is specially textured with a peen surface, which helps the molten iron adhere to the mold walls and prevents splashing. This reduces defects and ensures a smooth casting process. The casting time varies between 30 and 90 seconds, depending on the pipe size and class. After the iron solidifies, the pipe is cooled slightly in the mold before being extracted using a pipe puller mechanism. The sand core is broken up and removed, and the hot pipe is placed on rotating rollers to maintain its straightness and roundness before it moves to the annealing stage. This precise casting process produces pipes with consistent dimensions and structural integrity, preparing them for the heat treatment and finishing stages. Annealing is a heat treatment process crucial for achieving the desired mechanical properties of ductile iron pipe: ductility, strength, and toughness. After casting, the pipe is initially brittle due to rapid cooling in the mold. Annealing relieves internal stresses and transforms the microstructure into a more ductile form. Pipes are placed into a large natural gas-fired annealing oven, where the temperature at the entry point reaches approximately 1,750 degrees Fahrenheit, 954 degrees Celsius. The pipes move slowly through the oven on a conveyor system, allowing heat to penetrate evenly. As the pipes progress, the temperature gradually reduces to about 1,350 degrees Fahrenheit, 732 degrees Celsius in the cooling zone. The entire annealing cycle takes 35 to 45 minutes. This controlled heating and gradual cooling ensure the formation of spherical graphite nodules, essential for the pipe's ductility and strength. Quality control is a critical aspect of ductile iron pipe production, ensuring that each pipe meets or exceeds industry standards such as those set by the American Water Works Association, AWWA. The process involves continuous monitoring and testing at every stage, from raw materials to the finished product, to guarantee optimal performance and durability. Quality control begins with the selection and inspection of raw materials, particularly scrap metal, coke, and limestone. Samples of the raw scrap are tested for unwanted elements like tin, copper, and chromium, which can compromise the pipe's mechanical properties. This ensures that only suitable materials are used in the melting process. During melting, the molten iron is tested at multiple points to verify its chemical composition. Samples are taken from the cupola, after desulfurization and after magnesium treatment. These samples are sent to a melting lab for analysis using advanced equipment like spectrometers and infrared analyzers, which detect around 20 elements. Strict calibration standards are followed to ensure accuracy. This real-time analysis allows operators to make adjustments as needed to maintain the correct composition. Once the pipe is cast and annealed, it undergoes extensive visual inspections. Quality control personnel use floodlights and flashlights to identify surface defects such as cracks, inclusions, or irregularities. The dimensions of the pipe's bells and spigots are measured to ensure compliance with specifications, and each pipe is weighed to confirm it meets minimum weight standards for its class. If a pipe fails to meet these criteria, it may be reclassified or scrapped. Each pipe undergoes several mechanical tests to ensure strength and reliability. Hydrostatic testing. Pipes are subjected to water pressure of 500 psi for 5 seconds to confirm structural integrity and the absence of leaks. Tensile testing. Samples are cut from the pipe and tested for tensile strength, yield strength, and elongation. The tensile strength must reach at least 60,000 psi, and the pipe must demonstrate 10% elongation to meet AWWA standards. Impact testing. The Charpy impact test involves striking a notched sample with a swinging hammer. At room temperature, the sample must absorb at least 7 foot-pounds of energy without breaking. For extreme conditions, a test at -40 degrees Fahrenheit ensures the pipe performs well in cold environments, with a minimum threshold of 3 foot-pounds. Advanced testing. Microstructure analysis. Samples are examined under a microscope to confirm that the graphite nodules are spherical and uniformly distributed, an indicator of successful annealing. Hardness testing ensures the pipe's material meets specified hardness levels for durability. Ultrasonic velocity testing verifies uniformity and detects internal defects. Final inspection and finishing checks before shipment. Pipes are visually inspected again to ensure no defects were introduced during finishing. The cement lining and asphaltic coating are checked for proper application and curing. A reverse piece of duct tape is used to test the seal coat's adherence. Each pipe is marked with relevant information, including class, size, date of manufacture, and certifications. All testing data is integrated into a centralized computer system accessible to plant personnel. This system provides real-time updates and ensures all pipes are traceable throughout production. Any pipe failing quality standards is reviewed for possible rework or scrapping. The finishing process is the final stage in ductile iron pipe production, where pipes are treated, coated, and prepared for shipment to ensure long-term durability and performance. This phase includes cement mortar lining, asphaltic coating, curing, and final inspections, adhering to stringent industry standards. The interior of each pipe is lined with a cement mortar coating, which acts as a protective barrier against corrosion and buildup of deposits. The process begins with the placement of special caps on the pipe's bell and spigot ends to ensure the cement lining is confined to the interior. The pipe is rotated at high speed while pre-mixed Portland cement mortar is fed through a long trough that extends into the pipe. This rotation spreads the mortar evenly along the pipe's inner surface. The pipe is then spun at an even higher speed to compress the lining, ensuring a smooth and durable finish while forcing excess water to the surface, which is rinsed away. Both the interior and exterior of the pipe are coated with a thin layer of asphaltic paint or seal coat. This coating helps prevent flash rusting, enhances corrosion resistance, and seals the cement lining for proper curing. The paint is applied while the pipe is still damp, ensuring strong adhesion. After coating, the pipe is left to cure for at least 24 hours. During this time, the cement lining fully hydrates, achieving the desired strength and durability. Cured pipes are bundled and prepared for shipment. Before loading for delivery, pipes undergo a final visual inspection to verify the integrity of the coatings and linings. This ensures that each pipe meets the highest quality standards before leaving the facility.
Material receiving and alignment involves inspecting and verifying the quality of raw materials, such as steel plates, upon arrival at the facility. The materials are then aligned accurately on specialized platforms to ensure proper orientation for the rolling process. Rolling is the process of shaping the steel plate into a cylindrical form to create the pipe. Initially, the steel plate is fed through large rollers, which gradually bend it into a circular shape. This step requires precise control of pressure and alignment to ensure uniform curvature and consistent diameter along the pipe's length. The process may involve multiple passes through the rollers, with each pass incrementally increasing the curvature until the desired roundness is achieved. Proper rolling minimizes stress on the material and prevents defects like flat spots or uneven surfaces, which could affect the pipe's structural integrity. Confit up is a critical step where the edges of the rolled steel plate are carefully aligned and prepared for welding. This process ensures the two edges meet accurately, forming a continuous circular shape without gaps or misalignment. Special equipment, such as hydraulic jacks and clamps, is used to hold the edges in position and adjust them as needed for precise fitting. The fit-up process often involves tack welding at multiple points along the seam to temporarily secure the edges, preventing movement during the main welding process. Proper fit-up is essential to avoid weld defects, such as lack of fusion or excessive weld reinforcement, ensuring the final pipe meets quality standards for structural integrity and dimensional accuracy. The inside seam of the pipe is welded to join the edges together. Grinding involves smoothing the internal weld seam to remove any excess material and achieve a uniform surface inside the pipe. This process helps eliminate irregularities, ensuring better flow characteristics and reducing stress concentrations. Precision grinding also prepares the weld area for further inspections and quality assurance tests. Sol submerged arc welding, longitudinal, is a welding process where an arc is formed beneath a layer of flux, creating a strong, uniform weld along the pipe's longitudinal seam. Pipe assembly is the final stage in the pipe manufacturing process, where all components are brought together and prepared for quality inspection and subsequent processing. In this phase, individual pipe sections may be joined to achieve the desired overall length. This is typically done by aligning the ends of two or more pipe sections and using welding techniques, such as girth welding, to create a seamless connection. Proper alignment during this step is crucial to avoid misalignment issues that could compromise the pipe's structural integrity. After the pipe sections are assembled, a series of inspections is carried out to ensure dimensional accuracy, weld quality, and adherence to industry standards. These inspections may include visual examination, non-destructive testing, NDT methods like ultrasonic testing, and radiographic testing to detect any internal defects. The pipe's external and internal surfaces are also checked for uniformity, while measurements are taken to confirm the pipe's roundness, diameter, and length. Once inspections are completed, the pipe may undergo additional finishing processes, such as coating or painting, to provide corrosion protection and improve durability. The ends of the pipe may also be beveled, threaded, or fitted with special connectors, depending on the intended application. Sandblasting and painting involves surface preparation and coating to protect the pipe from corrosion. Sandblasting uses abrasive materials to clean the pipe surface, removing rust, scale, and contaminants for a roughened texture that enhances paint adhesion. After sandblasting, a protective paint or coating is applied, creating a durable barrier against environmental factors like moisture, chemicals, and UV exposure. The design phase involves creating detailed technical drawings and specifications using CAD software, ensuring structural integrity, compliance with regulations, and incorporating aesthetic considerations to meet project requirements and client expectations. Simulation utilizes software to model the steel structure's behavior under various conditions, predicting performance and identifying potential issues before fabrication. Flame cutting uses high-temperature oxy-fuel or plasma torches to precisely cut steel plates into required shapes and sizes for fabrication. After cutting, the edges of the steel sections are ground to remove burrs and achieve a smooth finish. Fabrication involves assembling the pre-cut steel components according to the design specifications. This step includes joining parts using methods like welding, bolting, or riveting. Skilled fabricators ensure accurate alignment and fitment, often utilizing jigs and fixtures for precision. Quality control measures are implemented throughout to maintain structural integrity and safety standards. Welding is the process of fusing metal components together using heat, typically generated by an electric arc or gas flame. Various techniques, such as MIG, TIG, and stick welding, are employed based on material type and application. To verify the quality of welds and materials, samples undergo destructive testing. Non-destructive testing, NDT, evaluates the integrity of welded joints and materials without causing damage. Techniques such as ultrasonic testing, radiographic testing, and magnetic particle inspection detect internal flaws, surface cracks, or inconsistencies. NDT ensures quality control, safety, and compliance with industry standards, allowing for reliable performance without compromising structural integrity. Dimensions check involves verifying that all fabricated components conform to the specified measurements and tolerances in the design. Accurate checks ensure proper fit and assembly, preventing structural issues during installation. Sandblasting is a surface preparation technique that involves blasting abrasive materials such as sand or steel grit at high pressure onto the steel surface. This process effectively removes rust, dirt, and old paint, creating a clean, rough surface. Sandblasting enhances adhesion for coatings and paints, ensuring better durability and corrosion resistance. Erection involves transporting fabricated steel components to the construction site and assembling them into the final structure. Skilled crews use cranes and other lifting equipment to position beams and columns accurately. This process requires careful planning, safety measures, and inspections to ensure stability, alignment, and adherence to design specifications during installation. Abasane Fiberglass, AFG, is a state-of-the-art ECR, e-glass with corrosion-resistance glass fiber manufacturing facility located in Salman Industrial City, Hid, Bahrain. Equipped with the latest technology, AFG specializes in producing high-quality glass fiber products for various industrial applications, including construction, automotive, and marine sectors. The facility's advanced manufacturing processes ensure superior quality and flexibility, enabling the production of a diverse range of glass fiber products to meet specific customer needs. AFG's product offerings include woven roving, assembled roving, chopped strand mat, and woven bands, all of which demonstrate exceptional strength and durability. The woven roving is engineered for applications requiring high tensile strength, while the assembled roving is ideal for reinforcement in resin systems. The chopped strand mat, known for its versatility, is suitable for various molding processes, providing uniform thickness and excellent surface finish. Additionally, AFG's woven bands are designed for specialized applications where precision and quality are paramount. The company's commitment to quality and innovation is reflected in its ongoing participation in international exhibitions and sales trips. AFG ensures superior quality through stringent quality control measures at every stage of the manufacturing process, from raw material selection to final product testing. The use of advanced technology and precise production techniques results in glass fiber products with consistent thickness, optimal strength, and excellent corrosion resistance, meeting international standards and customer expectations. These are protective layers applied to the interior or exterior of pipes to shield against corrosive elements and mechanical damage. The choice of coating depends on the specific environment and the type of stress the pipes will endure. A powder coating process where epoxy resin is heated and applied to the pipe's surface, forming a strong corrosion-resistant barrier. It's often used for both internal and external coating applications. Three-layer coating. This involves three distinct layers: an anti-corrosion coating, usually epoxy, an adhesive layer, and a protective outer layer of polyethylene or polypropylene. The combination provides excellent corrosion protection and mechanical strength. Extruded three-layer coating, similar to the three-layer coating, but the outer layer is extruded onto the pipe. This method improves adhesion and provides a consistent and durable protective layer, particularly for high-impact areas. Medium-density polyethylene, MDPE coatings offer good flexibility, impact resistance, and protection against chemicals. They are suitable for use in various soil types and environments. This involves applying a liquid epoxy inside the pipe, providing a smooth, corrosion-resistant surface that reduces friction and prevents buildup of deposits. An internal lining of cement mortar that provides a protective barrier against corrosive substances. It is often used for water and wastewater pipes due to its durability and compatibility with potable water. The manufacturing of stainless steel seamless pipes is a highly specialized process that ensures the production of durable and high-quality piping solutions for various industrial applications. Seamless pipes are characterized by the absence of welded joints, offering superior strength and resistance to corrosion. The process involves several critical stages, including raw material preparation, hot extrusion, and finishing, each contributing to the final final product's properties and quality. Skoda Tubes Limited, established in 2008, is a prominent player in the stainless steel pipe manufacturing industry, with a focus on producing seamless and welded pipes, tubes, and heat exchanger tubes. Over the years, Skoda Tubes Limited has grown from a small-scale operation to a global competitor, providing innovative stainless steel piping solutions to meet diverse market demands. Key steps in manufacturing stainless steel seamless pipes: raw material selection and preparation. The first step in the manufacturing process involves selecting high-quality stainless steel billets or bars. The choice of material depends on the desired grade and application, with common grades including 304, 316, and 321 stainless steel. The billets are carefully inspected for any defects or impurities which can affect the pipe's quality. Once selected, the billets are cut into appropriate sizes and prepared for the subsequent heating process. The prepared billets are heated in a furnace to a high temperature, typically between 1,200 degrees Celsius and 1,300 degrees Celsius. This heating process makes the material malleable and suitable for further shaping. After reaching the desired temperature, the heated billet is passed through a piercing mill, where it is subjected to rotary piercing. This process involves pushing the billet over a mandrel to create a hollow tube, known as a hollow shell or mother tube. The mandrel helps shape the billet into the preliminary pipe form, while rotary action ensures uniform wall thickness. To enhance the pipe's mechanical properties and corrosion resistance, it undergoes heat treatment processes such as annealing or quenching. This treatment helps in relieving internal stresses and homogenizing the material structure. After heat treatment, the pipe undergoes straightening, cutting, and surface finishing to meet customer specifications. Non-destructive testing methods, ultrasonic or eddy current testing, are employed to ensure the absence of defects. Finally, the seamless pipes are subjected to rigorous quality control checks. Tests include dimensional inspection, mechanical property evaluation, and corrosion resistance testing to guarantee compliance with international standards. The chain-making process begins with wire drawing, where metal rods, typically made from steel, aluminum, or other alloys, are reduced in diameter through a series of dies. This is done to achieve the desired thickness for the chain links. After the wire is drawn to the required diameter, it is cut into sections of specific lengths that will become individual links in the chain. The forming process involves bending these sections into the desired link shape, such as oval or circular. The wire segments are shaped using specialized machines that can precisely form the links while maintaining consistent dimensions and shapes. Once the links are formed, they need to be securely closed to ensure the chain's strength and durability. In the welding step, the two ends of each link are fused together, typically using electric resistance welding or laser welding. This creates a strong, continuous joint, eliminating any gaps or weak spots. Proper welding is essential to ensure that each link can withstand the stresses it will face during use. After welding, the chain undergoes heat treatment to enhance its mechanical properties, strength, flexibility, and wear resistance. The heat treatment process involves heating the chain to a specific temperature and then cooling it under controlled conditions. The final step in the chain-making process is testing, where the chains are inspected for quality and strength. This involves performing tensile tests, fatigue tests, and dimensional checks to ensure that each chain meets the required standards and specifications.